Okay, so carrying on from the stuff that we've done before, so we've been looking at the three conditions for static equilibrium, and we looked at this idea about representing forces using vectors, which are little arrows, and we talked about the idea that we need to balance systems. We draw simplified diagrams called free body diagrams, and then we have to make sure that the forces all balance and add up to zero on the different axes, so that the thing isn't moving. That's what structural engineers are interested in, making sure things don't move by making sure structures obey the three conditions for static equilibrium. Right, so we're going to carry on from that. What we're going to do is we're going to look at the third condition for static equilibrium. Now, the third condition for static equilibrium was the one about moments. Okay, all the moments around a point must equal zero, or the other way to express it was everything that's trying to rotate something clockwise must equal the sum of everything that's trying to rotate something anti-clockwise. Okay, that's the two different ways of stating the same thing. So what does that mean? So let's look at a free body diagram of a lever. So a lever is something that you might use to move a thing, right? A lever is designed to rotate. The whole point of a leverage is to make things rotate. So what you have is a point of rotation. So think of a seesaw, you know, a child's toy like a seesaw. It sits on a pivot, and it sits on what we call a fulcrum. Yeah, that's a point of rotation. Fulcrum. And if I apply an upwards force to this at some point a distance away, then this beam will rotate around that point, because there's nothing lifting at this side, it's only been lifted at this side, so the beam will rotate. And the idea is that we might do that to lift something heavy. So think of a wheelbarrow. Yeah. So in a wheelbarrow, you've got a wheel, obviously, and you've got the kind of the bit of the wheelbarrow where the load goes in. So that might be filled with stuff. Yeah. And that's joined on. The axle of the wheel is joined onto the wheelbarrow body there. And then you've got a handle that comes out here. So this stuff in here, all the debris inside the wheelbarrow, is acting down, and you provide a force up. Ooh. You provide a force up the way. And the whole system rotates around that little point of rotation in there. A wheel. Yeah, so it's like a wheelbarrow. There's a lever. You lifting a force up. So that one's pushing down and you're lifting it. So this statement here, the one about clockwise versus anti-clockwise. Okay, so this is referenced just in case. Yeah, just in case you don't know, because I know that we live in a digital age, right? You have clock faces, with the old minute hand and hour hand, yeah. And those hands rotate around the clock that way as time passes. That's clockwise, okay? So that's clockwise, and that's the opposite direction from clockwise. Oh, wait a minute, they're both the same. Yeah, so you get clockwise and you get anti-clockwise. There you go. So, in terms of this beam, we want to know which of these forces is trying to drive this thing clockwise and which is trying to drive it anti-clockwise. So I can see here that this would trace a circle that way around the fulcrum. So F2 must be trying to drive this thing clockwise, and this guy would trace a circle that way around the fulcrum. So this guy is anti-clockwise. Okay. So this is generating clockwise motion, and this is generating anti-clockwise motion. But what we need to be careful about here is that we're not talking about forces, we're talking about moments. Incidentally, see that wee O in there? That's wee pads really causing me bother. See that wee O in there? This guy here. That's a location. There. So that's like a little O letter of the alphabet that we're using to identify a place. So this condition says the sum of the moments around O equals 0. So around here. Right. And that's important because we're going to have to talk about distances. So this M stands for moments. So a moment, strange word that we use, right? It describes torque, turning force. Now, I'm using the word force here, but I'm not using force on its own. I'm using turning force. It's important that we include distances. Includes distances here. Okay, a moment is a mathematical thing. So a moment equals the force applied multiplied by the distance between the force and the centre of rotation. So in this instance, we've got this distance, and we'll get this distance. Yeah. There are two moments acting on this beam. I know that there are two moments because there's two forces. Okay, I know that one of the moments is a clockwise moment and one of the moments is an anti-clockwise moment. Straight away I can see I've got the ability to balance this system. So what this is telling us, what both of these things is telling us, is that this statement must be true. Okay, if we use this one, so the sum, I'm going to get lazy with these sigmas soon, that takes too long. The sum of clockwise equals the sum of the anti-clockwise. Now what's handy is I don't need to add anything up, don't need sums because there only is one of each. So the clockwise one is F2 multiplied by D2. That's the one and only clockwise moment. And then there's only one anti-clockwise moment, and it's F1 multiplied by D1. As long as that's true, as long as that force times that distance gives me the same number as that force times that distance, then this beam isn't moving. This thing is not moving. Does that mean the numbers operate? You know what I mean? So F1 is further away, but D1 is bigger. So F1 could be much smaller than F2, and this is actually the point of levers. You know, you could have a ton of bricks in there. If you've got a long enough handle, you'll still be able to lift it, because it's to do with moments rather than forces, right? That's what levers is all about. So we've got moments are force times distance to the centre of rotation. It's really important that you take into account that that distance is distance to centre of rotation. A lot of people make mistakes and start taking distances between forces, but it's not the distance between the forces, it's the distance to the centre of rotation. Moments can be done on their own. You can calculate a moment, so you can do force times distance, and you put units in at the end of that. The units of moments are the same as the units of torque. Newton meters. Or Newton meters for short. So what to do is let's do a really simple moments question. You wouldn't technically maybe be asked this type of question, but let's do it anyway, just so you get used to using the terminology. I'm going to give a 12 Newton force acting at a distance of 4 meters. And the question is, calculate the moment acting on the beam. I'll say lever instead of beam. So we go 12 multiplied by 4 equals 48 Newton meters. We would then round that to the correct number of significant figures. So 50 Newton meters to one significant figure. Now, I'm also going to state that the moment, that 50 Newton meters moment, is clockwise. Or I could just do that. Just a wee symbol that indicates clockwise. Now then, I want you to do these four in exactly the same way. Indicate the magnitude of the moment and indicate its direction, whether it's clockwise or anti-clockwise. I'm going to add one more in actually. Right, okay, so you go ahead and do those 5 questions and then we'll see what answers you get. We'll put that in an assignment and you can let me know what you get. Right, okay, so yeah, the idea is that you should be able to calculate a moment. Let's make it a little bit more complex then. So at the next point we're going to have more than one force acting on a beam. Right, so let's do that. Right, so 2 forces acting on it. 16 newtons, 32 newtons. Just put a couple of distances on here. 14 meters, 20 meters. And the question in this one would be, what is the total moment? What is the moment on this beam? So let's work out the moment on the beam then. So the moment on the beam is, and we need to be careful because they're going in different directions. So the moment on the beam is 16 multiplied by 4. That's our clockwise one. And then we've got an anti-clockwise one. So that means it's going to be minus 32 multiplied by, now what distance do you use? Remember, it's the distance to the centre of rotation, so it will be 20 plus 14, 34. This will give us the total moment because they're going in different directions. We're going to have to work out the clockwise moment and subtract from it the anti-clockwise moment. Anti-clockwise moments are getting negative signs in this case, and clockwise moments are getting positive signs. So the total moment equals, so 16 times 4 is what, 64, minus, I'm going to have to use a calculator for this one, 32 times 34, 32 times 34, 1088. Yeah. This is going to give me a negative number. 64 minus 1088 minus 1024 Newton meters. Now what does that minus mean? All that minus means is it's an anti-clockwise one. So again, I've got one significant figure in there. So that's 1000 Newton meters anti-clockwise. Yeah. So you need to pay attention to what's clockwise and what's anti-clockwise. Otherwise you'll end up getting the wrong answer, because I could have accidentally had a plus sign in there, which would have meant that this was much bigger. It would have been 1008 plus 64. At one significant figure it wouldn't have mattered, but Yeah, we need to be careful of this. So I'm now going to give you a bunch of questions that are calculate the total moment. Okay. Let me pause this and let me get the questions up. Okay, so remember and give clockwise moments positive signs and anti-clockwise moment negative signs, right? So in this first one you've got one clockwise and one anti-clockwise. In this one, you don't. Clockwise, it's also clockwise. In this one, the fulcrum's in the middle. You still need to figure out whether this one's clockwise or anti-clockwise, and you need to figure out whether this one's clockwise or anti-clockwise. And all I'm looking for is a total. So as long as you give clockwise moments positive signs and anti-clockwise moments negative signs, if you get a positive answer, that means that the total moment acting on that beam in that free body diagram, if you get a positive answer, it is clockwise, and if you get a negative answer, that means the total moment is anti-clockwise. Okay, you go ahead and do that then.